This lesson deals with a high-pass filter. You can find these notes in the course ebook in Chapter 6 starting on page 6. Given this RC circuit, let's solve for the output over the input in the frequency domain. It's a voltage divider since this current is the same as this one. It's R over R plus the impedance of the capacitor, which is 1 over j omega c. We multiply numerator and denominator by j omega c. I get j omega RC, and then just 1. Bring the v sub s over here, and again I have a transfer function, the output over the input. Let's plot the magnitude and angle versus frequency. The magnitude is the magnitude of the numerator minus the magnitude of the denominator. It's 20 log base 10 of the square root of the real part squared, which is 0, plus the imaginary part squared, which is omega RC, and then minus 20 log base 10 square root of the real part squared plus the imaginary part squared. Now we did this before, this was our last example. What's this? Let's just simplify this in terms of omega c again. I'm going to write this as 20 log base 10 of omega divided by omega c, where omega c is equal to 1 over RC in our particular example. And then we have minus this term. Let me write this as a plus of this quantity. In other words, we're going to take this quantity and add it to this quantity. Well, we've already sketched this. What does this look like? It depends on the ratio of omega to omega c. So if I let omega equal omega c, I have 20 log base 10 of 1, which is 0, or 0 dB. If I put omega equals 10 omega c, I have 20 log base 10 of 10, which is equal to 1 times 20, which is 20 dB. If I take 20 log base 10 of 1/10 omega c's cancel, I get 20 log base 10 of 1/10. That's the same as 20 log base 10 of 10 to the minus 1, which would be minus 20 dB. Now if you sketch these, they actually fall in a straight line. And you can see here the change in slope is 20 dB per decade. Well, this graph is going to be added to the one we did for the low-pass filter. Let's take a look at what that looks like. Here's our previous result, which was minus 20 log base 10 of the square root of 1 plus omega c squared. This was our low-pass response. And then we're going to add that to 20 log base 10 of omega c, which is just a straight line passing through 0 dB at omega equals omega c. I want to add these two curves up, this one and then this dotted one. If you add 0 to anything, you get anything back. Now when you get to this point, we're increasing at 20 dB per decade, and we're decreasing at 20 dB per decade. They cancel each other and we just level out. Given this high-pass transfer function, once you know the value of omega c, this will depend on your circuit. In our particular circuit, we're looking at 1 over RC. The sketch is just simply a straight line of 20 dB per decade, and then levels out at omega equals omega c with a slope of 0 dB per decade. Again, this is an approximation to the actual smooth curve. Didn't show the curve here, but it follows this asymptote and follows this asymptote. The worst error is about here, about 3 dB. Then you can approximate the magnitude at any given frequency by just reading off of this curve or just calculating where the slope is. And we can interpret this picture and interpret the circuit. Let's first take a look at the Bode plot. As the frequency approaches 0, this becomes more and more negative in dB. And 20 log of 0 is minus infinity dB. So as the frequency gets lower and lower with respect to omega c, never really get to DC here, we just get smaller and smaller by factors of 10, we're going to approach a gain of 0. We're going to block the frequencies. As the frequency increases beyond omega c, we approach 0 dB, and that just says that the output equals the input. We're going to pass higher frequencies compared to omega c. Now what does the circuit tell us? Really the same thing. Let's go back to the previous page. When the frequency approaches 0, this capacitor looks more like an open circuit. No current flows, and then no current flows in this resistor, and so we get 0 times R, and that gives V out equal to 0. As the frequency increases, the impedance of this capacitor gets smaller and smaller compared to R, and in the limit, as omega approaches infinity, it becomes a short circuit, and the output equals the input. The Bode plot and the schematic are telling us the same thing, different pictures, but telling us the same ideas. And this is helpful when we work on things in lab and we need to modify a circuit that we can kind of think about what's going to happen as we increase or decrease frequency. Let's go to page 8 and take a look at the angle response. Let's calculate the angle of our transfer function. The numerator was j omega RC. That's going to be the arctangent of the imaginary term, which is omega RC divided by 0. And that's going to be shooting off to plus infinity, and that's 90 degrees. And then the angle of the denominator is the arctangent of the imaginary term, which is omega RC divided by 1. And since we're taking the overall angle as the angle of the numerator minus the angle of the denominator, this is our total angle. And again, it varies with frequency, but this is the result we did for the low-pass filter. We're just simply adding this term. So let's sketch that. Here's our low-pass result. At omega equals omega c, we're at minus 45 degrees. If you go back a decade, you're roughly at 0 degrees. If you go forward a decade from omega c, 10 omega c, you drop 90 degrees. And then our second term is just 90 degrees, which is just this dotted line here. I'm going to add this constant to this one. I'm just going to lift it up. And knowing our transfer function, and knowing omega equals omega c, the phase angle response versus frequency as an approximation is 3 straight lines. Where at omega equals omega c, we're at 45 degrees. Go back a decade, we're at 90. Go forward a decade, we're at 0. And our slope here is minus 45 degrees per decade. 0 degrees per decade here, 0 degrees per decade here. If you know what frequency you're operating at, you can just go here and read off this value of angle and magnitude and get an approximation to that transfer function instead of solving for all of those tedious terms we did in Chapter 4. Again, it's an approximation, but a pretty good one. And lastly, this is the form of a high-pass filter. It's j omega over omega c divided by 1 plus j omega over omega c, where omega c can be whatever your circuit turns out to be. So we're just going to solve different circuits and solve for the value of omega c for inductor circuits, op-amp circuits, but there are various high-pass circuits. And this is a high-pass filter.